Hello and welcome to all students. In this lecture today we are study about the differentiation and the differentiability of scalar field. Okay, so let us start to our lecture. Now let us see the outline of our lecture. In this lecture, first of all we see some introductory part. After that we see Taylor's polynomial. Then we will learn about the definition of linear transformation and examples on linear transformation. So this is the outline of our lecture, our today's lecture. So in the introduction, we know that uh, in this chapter we will discuss about the differentiability of scalar valued function f from Rn to R. We know that a function from Rn to R is known as scalar valued function. Rn means Euclidean n space. Okay. Then we first understood the differentiability of function when n is equal to 1 using Taylor's polynomial for function f from R to R at x is equal to a. So here f from R to R means it is a function from set of real number to the set of real number. And we will see what is the how to derive a formula for differentiation for a real valued function from set of real number to the set of real number. Okay, so by using Taylor's polynomial. So we know the Taylor's polynomial. If f is a real valued function from set of real numbers to the set of real number, if f is a function from R to R is a real valued function, then Taylor's polynomial of function f at x is equal to a is given by f of a plus h is equal to f of a plus h into f dash of a plus h square upon 2 factorial into f double dash at a plus h cube upon 3 factorial into f triple dash at a plus dot dot dot. So here f dash denotes denotes the derivative of a function. F dash means first derivative of function f double dash means second derivative of function f, and f triple dash is a third derivative of function f. So this is the Taylor series expansion of a function f of a plus h, or we can say the expansion of a function about a in powers of h. इथं h च्या पावर्स आहेत म्हणून आपण त्याला expansion of a function f of a plus h about a in powers of h असं म्हणणार आहोत. Okay, so this is Taylor's series expansion, or we can say that it is a Taylor's polynomial in h, and it is equal to f of a plus h into f dash of a plus, आता या तिसरी जी 3 नंबरची टर्म आणि त्याच्या पुढच्या टर्म्स आहेत याच्यातून आपण h कॉमन घेणार आहोत. h into square bracket h upon 2 factorial into f double dash at a plus h cube upon 3 factorial into f triple dash at a plus dot dot dot. Okay, in the next step now, f of a plus h into f dash of a, first two terms are as it is plus h into, आता ही ब्रॅकेटेड क्वांटिटी जी आहे स्क्वेअर ब्रॅकेटमध्ये जी क्वांटिटी आहे त्या क्वांटिटीला आपण e ऑफ a, h असं म्हणणार आहोत, बिकॉज दिस ब्रॅकेटेड क्वांटिटी डिपेंड्स ऑन a as well as it depends on h also. Therefore we just give a notation E to this quantity, and E is a function of A and H, say. Okay, thus so that E, so if we observe that if H tends to 0, then E of AH, this term, will also tends to 0, so H म्हणजे H जर आपण H जसा 0 च्या जवळ जाईल तशी ही टर्म E of AH will also approaches to 0. Okay, so thus f of a plus h is approximately equal to f of a plus h into f dash of a. म्हणजे h tends to 0 याचं मिनिंग असं आहे की a plus h is approximately equal to a. Okay, so is approximately equal to a means value of the function f near to the point a is approximately equal to f of a plus h into f dash of a. That is the simple meaning. Once again, the value of function f near to the point a is approximately equal to f of a plus h into f dash of a. So this is geometric meaning of this Taylor's polynomial. We can write f dash of a. So from this previous slide, so see here, this is approximately equal to right hand side. F of a plus h is approximately equal to f of a plus h into f dash of a. So approximately equal to means when h approaches to 0, these two are approximately equal. So this is similar to say that f dash of a is equal to limit h tends to 0 f of a plus h minus f of a divided by h. So in this way, the formula for differentiation of a function f at point a is obtained. So formula for differentiation is obtained from the Taylor's expansion of function f about point a in powers of h. Okay, so that is very simple. Now we learn about the linear transformation, which is very much important when we study about the total derivative of the scalar valued function. Okay, so first of all we define what is mean by linear transformation. So we write the definition. Let capital V and W be vector spaces. A function capital T from vector space V to vector space W is said to be a linear transformation if it satisfies two conditions. If for all vectors xy belongs to V and for all scalars alpha in R, first condition is T of x plus y is equal to T of x plus T of y. Means when we operate the operator T on the addition of two vectors x and y, then we get addition of T of x and T of y. That is the meaning of this first condition. Second condition is T of alpha x is equal to alpha times T of x. So when we operate this operator T on alpha x, then we get alpha as a scalar outside and T is operating on the vector x. So if our function T satisfies these two conditions, then we can say that T is a linear transformation from the vector space V to vector space W. Okay, let us see some examples based on the vector space based on the linear transformation T. Let us see the example. Let t from R3 to R be a function defined as t of x comma y comma z is equal to 3x plus 4y plus 5z for all x comma y comma z belongs to R3. Show that T is a linear transformation. So first of all we understand the problem. Here one function is given and that function T is a function from R3 to R and it is defined like this: T of x comma y comma z. So T is operating on points on R3. So it has three components x, y, z. T of x comma y comma z. It is equal to, so its definition is given like this. So T of x, y, z is equal to 3 times first component plus 4 times second component y plus 5 times third component z. So definition is very simple. T of x comma y comma z is equal to 3 times first component plus 4 times second component y plus 5 times third component z. And it is true for all ordered triple pairs, ordered triplets x comma y comma z belongs to R3. Okay, and we have to show that the T is a linear transformation. Okay, to show that T is a linear transformation we have to verify the two conditions in the definition of linear transformation. So let us write the solution of this problem. Okay, while writing answer, first of all we write what first of all we write the given things. Given that t from R3 to R defined by t of x comma y comma z is equal to 3x plus 4y plus 5z, and it is true for all vectors x comma y comma z belongs to R3, belongs to R3. So in this problem our claim is to show that T is a linear transformation. To show that T is a linear transformation we have to verify the two conditions. We have to verify the two conditions given in the definition. Okay, to show that T is a linear transformation, we prove the two conditions which we have defined in the definition of linear transformation. So to prove these two conditions we need two vectors from the vector space R3. Let us take capital X is equal to x1 comma y1 comma z1 and capital Y is equal to x2 comma y2 comma z2 be any two vectors in R3. Let let alpha belongs to R be any scalar. Okay, so to prove these two conditions which we have defined in the definition, we need two vectors and one scalar, which we have taken here. Capital X is a one vector, capital Y is a one vector, another vector, and alpha is a scalar. So consider t of x plus y. So we try to operate the operator t on the addition of two vectors x and y. So and we see what we get. So it is equal to t of x vector is x1 comma y1 comma z1 plus y vector is x2 comma y2 comma z2. So inside the bracket there are two vectors and we have the addition of these two vectors. So we make the addition of these two vectors like this. So in the next step, t of x1 y1 z1 हा वेक्टर आणि x2 y2 z2 हा वेक्टर या दोघांची ॲडिशन नेक्स्ट स्टेपमध्ये आपण केलेली आहे. ती कशी केली बघा. फर्स्ट कंपोनंटमध्ये ॲड करायचा, सेकंड कंपोनंट ॲड इन टू द सेकंड कंपोनंट अँड थर्ड कंपोनंट ॲड इन टू द थर्ड कंपोनंट. सो x1 प्लस x2 कॉमा y1 प्लस y2 कॉमा z1 प्लस z2. तर अशा पद्धतीने आपल्याला addition of two vectors is again a vector. So addition of two vectors is again a vector. That's why we get again a vector. So t is operating on again a vector whose components are x1 plus x2 comma y1 plus y2 and comma z1 plus z2. So now operate t on this vector, but we know the definition of function t of x comma y comma z, and that definition is t of x y z is equal to 3x plus 4y plus 5z. So like this means 3 times first vector plus 4 times second vector plus 5 times third vector. So like this. So we here write the same definition for this vector: 3 times first vector plus 4 times second vector plus 5 times third vector. So 3 times x1 plus x2 plus 4 times y1 plus y2 plus 5 times z1 plus z2. आता पुढच्या स्टेपमध्ये 3ने ब्रॅकेटमध्ये मल्टिप्लाय करायचं आहे, 4ने ब्रॅकेटमध्ये मल्टिप्लाय करायचं आहे आणि 5ने ब्रॅकेटमध्ये मल्टिप्लाय करायचं आहे. ओके. सो इन द नेक्स्ट स्टेप we multiply inside the bracket. So 3x1 and we get 3x1 plus 3x2 plus 4y1 plus 4y2 plus 5z1 plus 5z2, and it is equal to, now in the next step we collect the terms having suffixes 1, means we take together 3x1 plus 4y1 plus 5z1 and take terms together with suffixes 2, means take together 3x2 plus 4y2 plus 5z2. Okay, so in the next step the meaning of these first 3 terms is nothing but t of x1 y1 z1. Okay, and the meaning of the last 3 terms is t of x2 comma y2 comma z2. So we write here. So first 3 terms is nothing but the definition of t of x1 y1 z1 plus last 3 terms is nothing but the definition of t of x2 y2 z2. Okay, but what is x1 y1 z1? It is vector x. And what is x2 y2 z2? It is nothing but vector y. So t of x plus t of y. So in this way we proved our first condition of linear transformation, t of x plus y is equal to t of x plus t of y. So thus we have t of x plus y is equal to t of x plus t of y. So now we will prove the second condition of linear transformation, okay, for this function. So for that, consider t operating on the vector alpha times x. Alpha is a scalar and x is a vector. X is equal to x1 y1 z1. Okay, so see what we get. It is equal to t of alpha as it is, and vector x is x1 comma y1 comma z1. It is equal to t of, now multiply by that alpha by scalar alpha to the vector x1 y1 z1. We know that how to multiply. So multiply by that scalar alpha to the each component of vector x1 y1 z1. So it is equal to t of alpha x1 comma alpha y1 comma alpha z1. Now again see here, t is operating on vector alpha x1 plus comma alpha y1 comma alpha z1, and we know the definition of t. So definition of t says that t of xyz is equal to 3 times first vector plus 4 times second vector plus 5 times third vector. So same thing we are writing here. So 3 times alpha x1 plus 4 times alpha y1 plus 5 times alpha z1. Now from these three terms we take alpha common. So if I take alpha common, inside the bracket we have 3x1 plus 4y1 plus 5z1. But this bracketed quantity is again nothing but the definition of t of x1 comma y1 comma z1. So it is alpha into t of x1 comma y1 comma z1, but x1 y1 z1 is nothing but a vector x. Therefore in the next step we write alpha times t of x. So thus we have proved, thus we also have t of alpha times x is equal to alpha tx. T of alpha times x is equal to alpha tx. So this shows that t is a linear transformation. So this is the way to show that any given function is a linear transformation. Just we have to prove two conditions given in the definition. Okay, so now let us write homework to you. In this we have given one question to solve at home. Let t from R3 to R be a function defined as t of x comma y comma z is equal to x plus y minus z for all x comma y comma z belongs to R3. Show that t is a linear transformation. So see here, that question is also very simple. No doubt all of you will solve this at your own. Okay, so try to solve this problem, and if you have any problem while solving you can ask me, no problem. And let us stop our lecture here. Okay, thank you very much.